In 2011, more than 20,000 people lost their lives, and hundreds of thousands of homes were swept away when a 50-foot tsunami crashed into Japan, leaving the entire world in shock. That devastating price forced Japan to build an enormous tsunami defense wall, stretching nearly 250 miles along the eastern coastline. But to construct walls towering almost 50 feet high and strong enough to absorb the impact of millions of tons of water, Japan had to mobilize tens of thousands of engineers, world-class machines, and construction processes calibrated down to the last millimeter. Yet one big question remains: can this concrete Great Wall truly protect Japan from the tsunamis of the future? Let's find out with Mandarin Tech. For decades, the northeastern coast of Japan has lived under a threat the entire world fears: the deadly combination of earthquakes and tsunamis. Japan sits right on the junction of four massive tectonic plates, a collision zone where the Earth's crust constantly grinds, slips, and produces more than 500 earthquakes every year. When these geological plates suddenly shift beneath the ocean floor, the entire seabed can rise or sink within seconds. That sudden deformation pushes up huge walls of water, creating tsunami waves dozens of feet high that accelerate toward shore with the force of millions of tons of water. In the past, small coastal towns were used to hearing red alert warnings over loudspeakers, and residents instinctively ran uphill the moment the ground started to shake. The disaster on March 11, 2011 was the most devastating proof of that danger. A magnitude 9.0 earthquake ruptured more than 300 miles of a tectonic plate boundary under the Pacific Ocean, generating a tsunami nearly 50 feet high, far beyond any defense Japan had ever prepared for. That wave swept away more than 20,000 lives, flattened over 120,000 homes, and triggered a major crisis at the Fukushima nuclear power plant. The old seawalls, designed only for waves up to 26 feet, were completely overwhelmed. Japan quickly understood that the earthquake was only the beginning. The tsunami was the true destroyer. So the country built nearly 250 miles of tsunami defense walls, each 50 feet tall, with foundations plunging 80 feet deep, a concrete Great Wall designed to buy precious minutes for people to evacuate before the waves arrive. More than 12 billion USD was invested not only in building the walls, but also in upgrading emergency alerts and evacuation routes. It was a simple yet powerful statement: tsunamis may return, but we will not let 2011 happen again. The first step in building Japan's massive tsunami seawall is lab research. Engineers collected all the data from the 2011 tsunami, then recreated the waves in artificial wave tanks and scaled down models to study how the water hit and overtopped the wall. After countless tests, they kept adjusting the height, thickness, and slope of the wall, as well as designing deeper foundations to prevent it from being pushed over when waves crashed past the top. Only when the models showed the best possible performance did they lock in the final design: a 15-meter wall with foundations driven 25 meters down, a wide trapezoid base, and a reinforced steel core strong enough to withstand an extreme tsunami. Once the design was finalized, the next step was to pinpoint exactly where this massive wall would be built. The nearly 400-kilometer stretch runs along the Tōhoku coastline in northeastern Japan, the region that took the full force of the 2011 tsunami. It extends continuously through the prefectures of Aomori, Iwate, Miyagi, and Fukushima, forming the longest and most unified coastal defense line in Japan's history. Once the exact route was finalized, crews began clearing the area, removing old houses, damaged infrastructure, power lines, and pipelines. At the same time, they built access roads, material yards, crane platforms, concrete mixing stations, and temporary drainage systems so construction could continue even during the rainy season. Much of the Tōhoku coastline sits on weak, sandy soil, so engineers first drilled detailed surveys and reinforced the ground. They installed deep concrete or steel piles, added layers of crushed stone and compacted sand, and stabilized the surface. The goal was to create a solid base strong enough to support a wall tens of meters tall without sinking, sliding, or cracking over time. Once the soil was stabilized, excavators dug massive foundation pits, in some sections going more than 20 meters deep. Near the shoreline, crews built temporary retaining walls or cofferdams to keep seawater out. After that, a base layer of concrete was poured, followed by dense steel reinforcement cages and large foundation blocks that formed an extremely heavy and wide foot to prevent the wall from being pushed over by powerful waves. Above the foundation, workers assembled tall, thick rebar cages based on the optimized lab design. Formwork was set in place, and concrete was pumped into the mold section by section. Each block, usually several dozen meters long, was poured, cured, inspected, and then connected to the next, creating one continuous barrier along the coast. On the ocean-facing side, crews installed special concrete units such as tetrapods, dolas, and other energy-dissipating blocks. These were stacked in multiple layers around the base of the wall to break the wave's force before it hit the structure. Some sections also used stepped faces, sloped surfaces, or splash reduction ledges to lower the height of water surges. On the landward side, soil and crushed rock were added along with drainage channels to prevent rainwater from pooling behind the wall. Many stretches include a walkway or inspection road on top, and in some towns the seawall even doubles as part of the local roadway. Railings, fences, safety ladders, and signage were added to allow safe public access. Note that this is only the general construction principle for the entire project. Because the seawall stretches nearly 400 kilometers, each area required minor adjustments in construction depending on the terrain, soil conditions, and coastal depth. But these variations were small and did not change the overall structure or design of the tsunami barrier. In some sections where the seawall needed extra thickness and impact resistance, crews added a layer of precast concrete blocks onto the outer surface. These interlocking panels were lifted into place by crane and arranged in a tight, uniform pattern to strengthen the wall and reduce erosion from constant wave action. Once secured, the tiles created a reinforced armor layer that helped the seawall withstand decades of pounding from the Pacific Ocean. In busy port cities like Iwaki, Japanese engineers had to design special entry points so ships could keep moving in and out. The first type is a top-down tsunami gate, built with a massive steel panel suspended between two concrete towers, operated by hydraulic motors and pulley systems. When a tsunami warning is issued, the steel panel drops down from above, sealing off the harbor entrance like a vertical wall that blocks incoming waves. In other ports, Japan uses a bottom-up rising gate, where the entire gate normally lies flat on the seafloor so ships can pass freely. When a tsunami approaches, a hydraulic system lifts the gate upward from below, locking it into the sidewalls to form a solid barrier against incoming water. This design is ideal for areas without overhead space for towers and allows marine traffic to operate 24/7 without obstruction. Because the gate stays underwater, it must be built with highly corrosion-resistant steel and fully sealed hinges to withstand constant pressure from seawater and sand. And that is the entire construction category to build Japan's tsunami wall. After completion, the nearly 400-kilometer tsunami seawall along the Tōhoku coastline became the largest continuous coastal defense system ever built in Japan. The project cost more than $12 billion, mobilized over 30,000 engineers, workers, and geotechnical specialists, and required thousands of heavy-duty machines operating nonstop for 5-7 years. Hundreds of wall sections were constructed simultaneously, each one requiring different foundation treatments, concrete structures, and reinforcement depending on the local terrain. Once operational, simulations showed that the new seawall system could reduce tsunami impact forces by 30–50% and provide several extra life-saving minutes for evacuation. Enough to save tens of thousands of people in a level 1 tsunami. Many coastal roads, fishing ports, and residential areas that were once wiped out are now far better protected, greatly reducing the risk of catastrophic damage when major waves strike. Although it can't stop every type of tsunami, this 400-kilometer barrier is considered Japan's final line of defense, giving the country more confidence against one of the most devastating natural threats on Earth. What about you? Do you think this massive seawall is enough to stop a tsunami? Let me know. We have compiled knowledge from many sources, so if there is anything wrong that needs to be corrected, please let us know in the comments section. But don't leave just yet. Japan's underwater tunnel construction technology is about to blow your mind just as much. In an environment that is completely isolated, under extreme pressure, and with geological conditions changing every meter, completing these tunnels stands as a clear testament to Japan's engineering capability and unwavering determination against the forces of the sea. In the modern world, underwater tunnels are a crucial part of transportation infrastructure, and Japan is one of the leading nations in this technology. Their undersea constructions connect islands, span deep bays, and create major breakthroughs in mobility, especially in regions where bridges or ferries can no longer meet growing demands. Thanks to these underwater tunnels, travel between Japan's coastal regions is faster, safer, and no longer dependent on weather conditions, while maintaining a steady flow of goods and people for the country's busy port cities. These tunnels have become vital economic arteries, boosting Japan's competitiveness and opening up new opportunities for development. However, building an underwater tunnel requires Japan to carry out meticulous preparation, detailed geological surveys, and near-perfect design precision to ensure safety and feasibility under the extreme pressure of the seabed environment.
The first phase begins with comprehensive seabed surveys. Engineers study subsea topography, collect soil samples, and analyze rock strata to determine the geological structure, the bearing stability of the seabed, and any latent hazards that could affect construction. Alongside the technical work, environmental considerations are prioritized throughout planning and design. The project team must assess the tunnel's potential impacts on marine ecosystems, ensuring species are protected and natural habitats are disturbed as little as possible. To achieve this, they implement noise mitigation measures during construction and may even install artificial reef structures to create new habitats for marine life. After the survey is completed, the construction step begins. The immersed tube method is one of the most widely used techniques for constructing underwater tunnels. The process begins with the prefabrication of massive reinforced concrete segments on land. Each standard element measures approximately 217 meters in length and weighs over 73,000 tons. These segments are manufactured with extreme precision to ensure perfect alignment and watertight sealing once submerged. Inside each segment, several compartments are designed for specific functions. 2 main chambers for highway lanes, 1 for a railway line, and another service corridor dedicated to future maintenance and inspection. Once the sections are complete, they are transported to sea and carefully lowered into pre-dredged positions on the seabed using floating pontoons and specialized cranes. Each segment is then joined sequentially to form a continuous tunnel of the required length. The most critical phase of this method lies in the joint connections. If the seals are not handled with precision, seawater infiltration could pose serious risks. To prevent this, rubber gaskets are inserted between segments to ensure watertightness, while layers of sand and gravel are placed above and around the tunnel to prevent buoyancy caused by water pressure. Only after the connections are securely locked and stabilized are the temporary end bulkheads removed, transforming the individual tubes into a seamless, watertight tunnel. However, this technique is only suitable for areas with a stable seabed and gentle water currents. In environments with strong turbulence or complex underwater terrain, the immersed tube method becomes impractical due to difficulties in anchoring and maintaining waterproof integrity. After construction is completed, the next crucial phase is safety inspection and operational assessment. In many modern projects, both submerged and underground tunnels are designed with 2 levels, effectively doubling traffic capacity without expanding the structural footprint. Drivers can maintain a stable speed of about 60 kilometers per hour, while emergency exits are positioned every 200 meters. Once the structure is fully completed, engineers carry out a series of rigorous tests, including waterproofing integrity, pressure resistance, fire safety, heating and ventilation performance, and overall structural stability. However, The journey of an underwater tunnel doesn't end once it opens. Maintenance is what truly determines its longevity and safety. Dedicated technical teams conduct regular inspections of the concrete lining, waterproof membranes, support frames, and drainage systems to ensure no deformation or cracking occurs over time. Hundreds of sensors installed along the tunnel continuously monitor pressure, temperature, humidity, and vibration, transmitting real-time data to a central control room, where engineers can detect even the earliest signs of structural fatigue. In parallel, cleaning and sediment removal are carried out periodically using specialized vehicles equipped with high-pressure water jets and suction systems to keep the tunnel floor clear and prevent blockages. Through the combination of advanced sensor technology and precise manual maintenance routines, today's underwater tunnels can operate safely, efficiently, and sustainably for decades, enduring the harsh environment of the ocean depths while remaining a testament to human engineering resilience.
You've now explored how Japan builds some of its most impressive ocean-facing megastructures. From massive tsunami seawalls to deep undersea tunnels, these projects showcase not only Japan's advanced engineering, but also the resilience of a nation that always rises after disaster. Stay tuned for more videos as we continue exploring incredible mega projects from around the world.